All right, we are back recording. Let's go on part three. Fundamental force underlying all chemical reactions. All right, so the answer is electrical. Here, let's go back to this graphic here. Look at why. Right. So in physics, there are considered to be four fundamental forces, and here they are: gravity, electromagnetism, strong and weak nuclear forces. Right. Now, strong and weak nuclear forces, we'll talk about when we get to the quantum mechanics part. Right. In this class, we mostly have done the top two. And weirdly enough, since we just covered relativity, you guys remember there's even a perspective within relativity that gravity shouldn't even be considered one of these fundamental forces, but or that's a little separate. Right? But for like a basic physics one class, the main two forces you care about are these top two: gravity and electromagnetism. Right? Electromagnetism accounts for pretty much everything significant at a macro scale that's not gravity. Right? So like if you just pick up your pencil and start writing with your pencil, I say, oh, okay, well I see like normal forces and this force that. Right? But really, it's electrons pushing against electrons, so it's electron fields. Right? So that's all under the umbrella of electromagnetism. Right? Yeah, so we're jumping right into the electricity part. So this could set electrostatic forces, right? And then once we get those flowing, then you have currents and nothing. All right, what's at the board? To be safe in the unlikely case of a lightning strike, it's best to be in a building framed with. Uh, yeah, answer steel. Truth be told, I miscovered that in the class a few weeks back. Right? But this is called a Faraday cage. What's this called? Faraday cage. Right? See this kid inside this metal cage, right? And it's being zapped with lightning. Because doesn't the electricity want to follow the path of least resistance? And exactly. Yeah, what's more conductive than what, right? Because if this electricity sees this metal and says that's the path of least resistance, doesn't the electricity definitely want to follow that steel frame? Yeah, steel frame right into the ground, right? And then whoever's inside the frame is safe because the electricity does not want to go through you, right? But guys, if you were inside a wood framed building instead, wood framed, right? Now the electricity is looking for path of least resistance, and the wood is not very conductive, right? You might look more conductive to the electricity than the wood frame would be, and now the electricity is going through you, and trying to get through the ground to the ground that way. Right? Yeah, so you're better off in a steel frame. It's called a Faraday cage. Okay? Do you guys think that modern day buildings are all designed with this principle? Do you guys think you're sitting inside a steel frame building right now? Right? Yeah, Florida, lightning capital of the world. So if lightning strikes this building, it's going to follow the steel frame right into the ground. Yeah, so in case of a lightning strike, you're safe indoors. Right? Now, if you go back a few hundred years ago, that wasn't always the case, right? So Benjamin Franklin invented something called a lightning rod. It was kind of a predecessor to this. So people 100 years ago would notice that a lot of church steeples would get struck by lightning, right? Because that would be like, it's tall, pointy, maybe like the tallest point in town, tall point, right? So that would attract a lot of lightning. And then that would burn down the churches. But Ben Franklin said, oh, if you just put a steel rod up there and then have a wire go down to the ground, then that would be the path of least resistance. It's going to stop all these buildings from burning down. Yeah. And nowadays we have steel frame buildings. Two charges separated by 1 meter exert a 20 Newton force on each other. If the distance is double, the new force will be. So we're going to double this distance. Guys, what's the factor of 2 squared? What is 2 squared? It'd be 4, right? Right. And it's 1 over that. So it would be a quarter of the force. Well, what's 1/4 of 20 newtons? Hey, 5 newtons. Right. Here, I'll go over again. Right. So this is electrostatic force. Electrostatic force. So look at this. So what's the force between these two charged particles? Right. Q1 and Q2 are the charges. Right. D is the distance between them. Right. Notice it's 1 over the distance squared. That looks a lot like universal gravitation, doesn't it? Right. Except instead of universal gravity constant, we get this electrostatic constant. That's what this blue K is right here. It's just this number. Right. Right. But here, this is a proportional question. So if you have double the distance between two objects, right, I'm throwing a factor of 2 on that D. It's that factor 2 is also getting squared along with the D. Turns it to a 4 down here. So okay, so it'd be a quarter of the force. Well, if the original force was 20 newtons, a quarter of that is 5, so it'd be 5 newtons. Right? You guys see how proportions are going to work like that, right? And if this was a gravitation question between, say, a planet and its nearby moon, the answer would be exactly the same. Electrical resistance in a wire. Ooh, do you guys remember that Plato lab? Oh, there it is. Right, you guys were running currents through the Plato. Right. So what does resistance end to end depend on? Yeah, all of those factors, right? It's all in that equation right there. Hmm. So the longer the wire, the more the resistance from end to end. I think that makes sense. You have a wire that's like 10 kilometers long versus 20 kilometers long. Right? Cross-sectional area. So the thicker the wire, the less resistance. Ah, okay, that's where we're dividing by the cross-sectional area. And this rho is resistivity. Do you guys remember for Plato, what did you guys get? Like 0.3 ohmmeters or something like that, right? Okay. And then uh, aluminum would be way more conductive than Plato would be, right? And copper is even better. Right? I think silver is even better than that. But, all right, so different materials, different properties. Compared to thin wires, the electrical resistance of thick wires, yeah, is not as much. Not as much. There's less resistance in a thicker wire. Right? Say if you make this cross-sectional area really, really, really big, now you're dividing by a big number. Okay, so the overall fraction becomes smaller, so that's less resistance. Ah, right. You could do a traffic analogy. What would be easier to drive on, a two-lane road or a six-lane road? Right. So the six-lane road is going to be able to uh, carry more traffic. There'd be less resistance to the flow of traffic. Primary reason a bird can perch harmlessly on bare high voltage wires. Yeah, there you go. No potential difference. Also called voltage. There's no voltage. Right? So if his right foot is sitting on 10,000 volts and his left foot is also sitting on 10,000 volts, the difference is zero. Right? If there's no potential difference, there's no voltage. This V goes to zero. Right? Potential difference. Okay, so then the current is also zero. Yeah.
Does that mean if like there's a wire and I grab it both at the same time, nothing would happen?
As long as your feet are not on the ground.
Yeah.
Yeah. Okay. Now, if your feet touch the ground, then now the current's going to go through you and into the ground. Right. But
Okay.
if you jump up in the air and grab the wire, right? Yeah. In principle, you should be okay.
So
Yeah.
just don't try.
That's the best option is to not try that. Yeah. Right. Yeah. Yeah. Uh, an 8-volt battery connected to a resistor, 2 amps of current in it flowing. What's the resistance? Right, so we just put 8 volts right here. Here's 8 volts. We got 2 amps of current flowing. That's where the I goes, is 2 amps. So 8 divided by what is equal to 2? You guys see that? 8 divided by what is equal to 2? Yeah, 4 ohms. There you go. Yeah. So that's called Ohm's law. Right, so you guys can navigate Ohm's law. Right, so no Ohm's law. Current is voltage over resistance. When connected to 110 volts power supply, how much current is in a bulb that has a resistance of 220 ohms? Did you guys do 110 divided by 220? Yeah, half an amp. Okay, so 110 over 220. Okay, so back-to-back Ohm's law questions. Ohm's law. Right here, say that again. Right. So the resulting current is equal to the potential difference or the voltage divided by the resistance. Oftentimes textbooks also write this as V equals IR, so you might see the non-fraction version of that. Light bulb plugged into 120 volts outlet has 0.7 amps current in it. What is the power rating in the bulb? Ooh, give you voltage and current. Yeah, 84 watts. Right. Right, so you guys did this top formula right here. P equals IV. Power is current times voltage. Is IV. If you had solved for resistance first, you could have used these other equations. They would still give you 84 watts of power. So you guys go with 84 watts of power. Right, P equals IV is a good one. A closed circuit is a circuit in which charge. Can't flow. There you go. Okay. So if somebody mentions an open circuit, that means the charge cannot flow. If it's a closed circuit, now there's a complete path for the electricity and it can flow. Current can flow. Right? Of course, if it's hooked up to a battery, then right, we're going from one end of the battery to the other end of the battery. Right? So if you hit the on switch here, you close the circuit. Everything turns on. Right? So if your appliance is running, it's a closed circuit. Yeah. As more lamps are put into a series circuit, the overall current. Okay. Probably should give you guys more time for that. Okay. Because this is kind of a two-part problem you have to think about. Okay. The middle question is what happens to the resistance? Okay. As you put more and more bulbs in series, what happens to the overall resistance? Yeah, the resistance gets more and more and more. Okay. Then you switch over to Ohm's law. And you say, I remember current is voltage divided by resistance. So since the resistance is increasing, the overall current must be decreasing. Hey, here's another way to think about this too. You guys remember you guys had those Christmas lights, or Paul Hewitt had his version with his car battery. So you guys are just. You guys remember if you put more and more and more bulbs in series like this, what happened to the brightness of the bulbs every time you added on? Yeah, it got dimmer and dimmer and dimmer, didn't it? Right. That would also kind of hint towards this. Yeah, yeah. That, anyways, think about that. As more lamps are put into a parallel circuit. Ooh, now what? Parallel. The overall current. Okay, awesome. Guess all got that. Okay. Now, here's a couple ways to think about that. Okay. One way is exactly the opposite of the previous question. As you add more and more bulbs in, or resistors in general, in parallel, the resistance of the entire circuit decreases. Right? And if the resistance decreases, then the resulting current would increase from the same battery. Right? But here's a different way to think about it. When you guys had your Christmas lights, because when you had those lights and you started stacking them like rungs of a ladder, suppose the first one you put on is really bright, and then you put on the second one. Did the first one stay equally bright? Yeah, it sure did. Okay, now you have two bright bulbs. Then you put on a third one. Now are all three really bright? Yeah, yeah. Right. Because they're all getting the full voltage from the battery. Like if you have a 9-volt battery down here, they're all getting all 9 volts. All of it. Right? Okay. So it's like every time you put on a bulb, now you're opening up a new path for the current to flow. Right. So you put on one bulb, the current flows. You put on a second bulb, now the current doubles from what it started. You put on a third bulb, now you got 3 times the current. Because it's got to supply those 3 bulbs. Right. Yeah, so the more bulbs you put on in parallel, the current supplied by the battery has to increase. Okay. You guys get there. Get there. Uh, one bulb in a series, so back to series, circuit burns out. Yeah, none of the other bulbs are going to light up at all. Now, let's go to that picture and look at why. None of the other bulbs are even going to light up. Right? Say if, how about this resistor B? This bulb just burns out right here, burns out. Okay. Doesn't that open the circuit? And now there's no path for the current to flow through at all. Right? Okay. Let's do a little traffic analogy. What if you have to drive around town and get back to this parking garage, represented by this battery here, this parking garage, right? And you have to go through this stoplight, this stoplight, this stoplight, right? But this stoplight, well, for some reason, you can't get through this one anymore. Maybe road's blocked. Who knows? There was an earthquake. You can't drive on this road anymore. Well, that means you can't drive at all. Right? You're just stuck in the parking garage. Right? So no current's going to flow. Guess that. Right? Now none of the bulbs even light up. Right? Right. How about the parallel version of that question? Parallel. Okay, same as before. Same as before. Okay. Uh, remember a few minutes ago we were saying if you construct this from scratch, so you put on one bulb, it's bright. You put on a second bulb, now you have two bright bulbs. Put on a third one, now you have three bright bulbs. Okay? But the brightness doesn't ever change for a single bulb. The brightness ever changes. Right? Well, if you just do that process in reverse, you start taking bulbs off, then the other ones are still unaffected. Right? Or if one burns out, like this resistor B right here burns out. Right? Same thing. It's just like, okay, well now you have two instead of three, but they're in parallel, so they each get the same voltage as before, the same current as before. Yeah. Okay. Um, right, let's do a little traffic analogy. What if you want to drive around town with this city grid right here? Right, so here's your parking garage down here with the voltage source. There's your parking garage. I'm gonna leave the parking garage, start driving around. Right? Well, now I have some options. I can drive down any one of these streets and then get back to the parking garage. Right? So if I'm no longer able to go down street B for whatever reason, well, that's okay. I can still go through A or C. Let's still do that. Same as before. Right, you guys good with that one? Same as before? A short circuit. 'Yeah, the positive is connected directly to the negative, right? Or you could say that there's no significant resistance, there's no resistance, right? Like, ooh, did I tell you guys if you take a paper, like a non-insulated paper clip, just a bare wire paper clip, and you touch that across the leads of a 9-volt battery, right? So some of you guys may try that. What happens with the paper clip? Get, yeah, it gets very, very hot very fast. Yeah, 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 right? Because that wire is acting as a short, and it creates a short circuit. Now you're draining the battery very quickly, so all that energy is run through the paperclip. That's why it heats up real fast. Right? So the process won't last very long. But right. Short circuit, right? So that's of course normally something that you want to avoid, right? Right. If you guys want your phone to your cell phone to fall in a glass of water, ooh, that would be bad, right? Because now that's creating pathways for the electricity to flow where it's not supposed to. It's going to short out your phone. The total resistance of 10 ohms and 7 ohms in series. $17. There you go. You just very simply add them up. Right? As long as they're in series, you can just add them up. 10 and 7, 17. Right, so you guys know you can add the resistors. You guys good? That's good. Yeah. I think everybody got that, right? You guys okay? You guys good? Yeah, all right. Now what about parallel? Let's go 6 ohms and 12 ohms in parallel. Huh. Okay, so 6 and 12 in parallel makes 4 ohms. Right. Let's look back at the circuit. I see some resistors in parallel, and here's a good equation here. You could do fractions, that's fine. If you just have two resistors at a time, it's common to use this product over sum method. Right? So you guys have calculators within reach, right? Try this out if you didn't before. Do 6 times 12. Guess what is 6 times 12? 72. And then what's 6 plus 12? 18. Right. So guys, what is 72 divided by 18? Yeah, it's 4 ohms. Okay. Hey, can I change the story a little bit? What if you and a friend are painting a fence? Ah, do you guys remember this? Right, and now you're working in parallel. You're both painting the fence at the same time. You're helping each other out. It would take you 6 hours by yourself. It would take your friend 12 hours by himself. Right. Now, if you work together, does it make sense that the total time for both of you has to be less than 6 hours at least? Yeah, and it turns out it would be also 4 hours, right? It's the same math, right? Right, you guys can do working in parallel, resistors in parallel. This good. All right, resistors in parallel. There you go. If you break a bar magnet in half, each half. Yeah. Okay. Well, we'll get a new north-south pole. Yeah. So all magnets, all conventional magnets, yeah, they're gonna have a north pole and a south pole. There are no unipolar magnets, north and south. Right. Break a magnet in half, it still has a north and a south, north and south. Device consisting of a coil that is mechanically rotated in a stationary magnetic field. That's one of those. Okay, so we're talking about a generator here. Let's look at that picture again. Right. So there's two devices here. They're really like physically basically identical, but they do opposite processes. Right. So this question is framed like this picture on the left. So when it says a coil is mechanically rotated, that's referring to this waterfall and this waterfall wheel. You guys see this water wheel right here? Right. So that's like mechanical energy. This is like pushing forces, potential and kinetic energy, that sort of thing. That looks like this water wheel, right? So that's going to force this coil to turn in the stationary magnetic field, right? Which induces a voltage and therefore a current. Right? And now that energy that used to be in the falling water has been transferred onto this electric grid in the form of electric currents. And, okay. Uh, Now there's another half of this process, which is okay. Well, now we've got all this energy on the grid. What are we going to do with it? Right. Now, if you run that current past another magnetic field, it induces a force, and that was do you guys remember that was the motor you guys created? You guys created some motors. You guys remember that? Right. I gave you guys magnets and batteries and wire, and I think that was it. Right, just that. Right? Yeah, and that induced a force, and then it just started spinning. Boo! That's how a ceiling fan runs. Right, so this is a generator. Okay, and there's the opposite question. A device that transforms electrical energy back to mechanical has to be called a. Yeah, there you go, motor. So you guys go with a generator and a motor? Most commercial generators are driven by. Yeah, the answer is steam. Yes, steam is the vast majority. Okay, so here's your power plant. Uh, you boil water, water turns to steam, turns a turbine, right, which forces a wire past a magnet, and that generates electricity. We got electricity on the grid, right? Meanwhile, that steam has now been depleted of its useful energy, so it's condensed back to just very hot water, and it's pumped back around and it's boiled, and that process repeats. Right? Hey, now, you could use a lot of different fuel sources to boil the water. You could use coal, you could use natural gas, you could use nuclear, right? There's a lot of ways you can boil the water, right? But yeah, the vast majority of electricity is through some version of that process, right? And then yeah, wind energy is of course an exception. That's only a tiny percentage of the electricity on the grid. Same thing with solar. Solar is an exception, but that's not a huge percentage. Light is, oh, here we go. This looks like quantum. Oh, never mind. Sorry, this is relativity. Relativity. We talked about this. Same code. Well, it's probably not the answer then, right? Yeah, same speed. Yeah, you guys remember theory of relativity? Right. Remember, light always has the same speed, regardless of your frame of reference. Even if you're in a rocket ship moving at half the speed of light in some direction, you still perceive the speed of light as the speed of light, the same as someone in a different frame of reference. Okay?
I thought you said it when it's in water, it moves slower.
Yeah, that's true. Yeah, that's true. Yeah. Okay, so a lot of these are simplified a little bit. Yeah, so like through a vacuum, that would be true. Yeah, no, you're right. Yeah, when light hits the water, it does slow down, or when light hits glass, it slows down. Right, but through a vacuum. So yeah, the different frames of reference, you can be moving very fast or very slow, or not moving at all. Right, everybody still agrees on the perceived speed of light. Right, so speed of light's the same everywhere. Universal constant. Einstein reasoned. Yeah, there you go. All the above. All motion is relative. A spaceship can only measure its speed relative to other objects, not to empty space. Yeah, yeah, right. Which was a complete break in thinking from like before 1905. Right. Right. Spaceship moves away from a space station at half the speed of light. A person in the space station flashes a light beacon. People in the ship will see light traveling toward them at. Yeah, there you go. Speed of light. Right. Now, if you applied Newtonian thinking to this, like if you went back to like pre 1905 and asked most people what the answer should be, or scientists, right? The Newtonian answer would have been half the speed of light, right? But Einstein says, no, that's not actually true. Actually, everybody sees the speed of light, right? And you guys got that. Right, that's relativity. Twin paradox. Earth twin views rocket twin's clock as running. Ooh, it's this green hat guy is looking through the window at this red clock and sees it running what? Yeah, slow. Yeah. Okay. You guys remember Rocket Twin aged very slowly and stayed young, and then Earth Twin turned into an old man? Okay. So that's the story version of this. Okay. And then the equation version is in this box right here. So this equation backs that story. They all go hand in hand. Yeah, same thing. So if you speed up, your clock slows down according to an observer in an inertial frame of reference. To calculate how much rest energy an object contains, yeah, E equals mc squared, mass times the speed of light squared. That's the energy of nuclear reactions. Right, so you guys go with the energy of nuclear reactions, E equals mc squared. Energy is mass times the speed of light squared. If Einstein's equations for special relativity are valid, yeah, all the above. Right? That's called the correspondence principle, right? Which is that even if you slow down to non-relativistic speeds, like less than 5% of the speed of light, right? Einstein's equations should predict what Newton was already predicting for those scenarios. It's like, oh yeah, it all lines up, and it says about the same thing. Yeah, correspondence principle. Here we go. These are the quantum questions. Okay. Light behaves as, take a guess. Uh, yeah, so is light a particle? Is light a wave? That was a debate in science for hundreds of years, and there was a back and forth and a whole story. Okay. But the modern day version of this is, well, it actually has properties of both. Right? Same thing for electrons. Same thing. You can make a case for a lot of things. Is something a particle, a wave? Things get kind of fuzzy when you get to quantum mechanics. It's hard to put things in a box anymore. Even cats. A photocell can be activated with a blue light, but not a red light. This is because blue light has, again, take a guess here. Maybe that graph helps out, possibly. Yeah, blue light does have a higher frequency than red light or a shorter wavelength. So you guys know that red has a long wavelength and a low frequency, and then blue is the other end of the spectrum. Blue has a short wavelength and a high frequency. Okay. But they're all traveling at the same speed, aren't they? Which is the speed of light. Yeah, it's a higher frequency. Right? And so it turns out that beyond the threshold frequency, right? Say if you double the frequency, you can double the amount of energy that you can capture on a solar cell. Right? And that was really weird when people first figured that out. Actually, this is what Einstein won his Nobel Prize in physics for. Weirdly enough, it wasn't for theory of relativity or anything he's best known for. It was for discovering that. The wavelength of a particle. Ooh, take a guess. Yeah. Okay. So called the de Broglie wavelength. Okay, so you guys will see that in the next week or so. Discrete orbits of electrons are best understood by considering the electrons. Okay, so I was looking for wave properties there. Right. Right, so if you have a model in your mind of an atom looks like kind of like a solar system, and the electrons are whizzed around the nucleus, like planets around a star, right? Um, that's a model that is partially correct, but also partially incorrect, right? Right. So in quantum mechanics, a lot of properties of atoms and therefore all of chemistry can be explained by this wave nature of electrons. Right? So electrons have to complete orbits around the atom. Nuclear fission. Um, yeah, so looking for electrical forces inside a nucleus to overpower the nuclear forces. Right. So what could initiate that? Well, that was a big part of the Manhattan Project, right? How do you get that fission process to occur? So electrical forces overpower nuclear forces, right? They're gonna take large atoms and split them and get energy out of it. Nuclear fusion releases energy when this part here. Yeah, very light nuclei fuse together. So a lot of the attention right now is on these particular isotopes of hydrogen, right? So deuterium and tritium, right? Hydrogen with extra neutrons, right? Uh, if uh, if you can fuse those together, you can get an enormous amount of energy, like hundreds of times, almost 1,000 times the energy that you can out of this fission reaction. Yeah. And so, can we turn that into a power plant? Hopefully, in our lifetimes, because that would be a really good tech. Primary fill for a nuclear fusion reaction is hydrogen. Okay, so you guys saw it was this right here, right? Hydrogen, different isotopes of hydrogen. Fusion, hydrogen. Right? Uranium is the fission one. So uranium, think fission. Hydrogen, think fusion. Right. And last question. You guys ready for the last one? Nuclear process that has relatively few radioactive byproducts. Yeah, is fusion. So all modern day nuclear power plants run on fission. Of course, one of the problems with fission is you get this nuclear radioactive material that you have to, as waste product, you have to figure out how to store for tens of thousands of years, with where it doesn't affect the environment or other people. Right? But if you can use fusion instead, then that's a lot less of a problem. All right. We got some winners. So good job, guys, and yeah, hope you guys have a good weekend, and we'll do quantum mechanics next week.